This video is sponsored by Brilliant.org. More about them later in the video. Photons have energy, and according to Einstein, E equals mc squared. So I thought that photons' energy can be converted into mass, and so therefore they should have mass given by E by c squared. But what I read and heard from everyone is that that's wrong. Photons are massless, and I never understood why. The reasons I got was because this equation doesn't apply to photons. But why? Because photons travel at the speed of light c. What? It felt like these were all disconnected, empty statements. I never got a true intuitive understanding behind what's really going on over here. But then I understood the problem. The problem was I hadn't really understood what E equals mc squared was. But then I read up, not Feynman lectures, because Feynman lectures also didn't help, and you'll see why towards the end of it. But after reading a lot of it, I finally understood what it was, and then I got the complete picture, and now I feel like I have a much deeper intuition for what's going on, and I'm super excited to share that with you. So the promise of this video is we will attack this problem from different angles, and by the end of the video, if I do this right, you will walk away with a much more profound understanding of what's really going on. So if you're ready for this, let's begin. So where do we start, Einstein? Well, Einstein is saying, because we want to talk about light's mass over here, let's take a step back and ask ourselves the big question: what exactly is mass? Well, I tell Einstein, well, mass is just the amount of stuff. And Einstein says there's a problem with this. And I'm like, why, Einstein? To answer this, he asks me, Mahesh, what is your body made of fundamentally? Well, I say, well, it's made of atoms. But he says, Mahesh, at the most fundamental level. Oh, I say, oh, all right, yeah. It's made of protons, neutrons, and electrons. And he says, Mahesh, at the most fundamental level. That's right, protons and neutrons are made of quarks themselves. So Einstein, at the most fundamental level, my body is made of quarks and electrons. Now Einstein says, okay, now if a mass is the amount of stuff, then my body mass must equal the mass of all the quarks and electrons, right? I say, yeah, but turns out that's not true. Turns out if you add it up, then the quarks and the electrons add up to give about 1 to 5% of my total body mass. And different papers cite different numbers, so I don't know exactly what percentage it is. But the important thing is the total quarks and electrons only add up to give me a fraction of my body mass. And so I'm asking Einstein, well, where does the rest of my mass come from, Einstein? Well, Einstein says these quarks are held together by energy inside the atom. And the quarks themselves are vibrating, so they also have this kinetic energy. So if you take all of that energy, you add it all up, and you divide that energy by c squared, that gives you the rest of the mass, Mahesh, he says. Wait a second, Einstein, are you saying that energy is converted to my mass? And Einstein says, no. There is no conversion business over here. In fact, what he's saying is that a better way to think about it is that there is no such thing as mass at all. What we have been always measuring is energy divided by c squared. And I find that pretty mind-blowing, because I used to think that energy converting into mass is mind-blowing, but it turns out the reality is much, much more profound. There is no conversion. Now it makes sense, because there is no such thing as mass. There's only the energy, and you're always weighing, you're always measuring the energy. Wow. But wait, we have some questions. Einstein, what about that 1%? What about the mass of the quarks and the electrons themselves? Where do they get their mass from? Well, Einstein says these quarks and electrons, well, it turns out that they interact with something called the Higgs field, and that interaction gives them the energy. So when you're measuring the mass of electrons and quarks, what you're really measuring, again, is their energy divided by c squared. You are always, even at the most fundamental level, measuring energy. No conversion, no such thing as mass. It's always energy divided by c squared. That's what his equation really means. All right, let's see if you're on the same page. Einstein, if I understand you correctly, are you saying that if I take a spring and I compress it, then compressing it gives it an additional potential energy, and because of that, it gets more mass? And Einstein says, yes, that's E equals mc squared. Whoa, all right. What if I take a cold coffee and I heat it up? Does that heating gives it more vibrational kinetic energy, and does that give it more mass? And Einstein says, yes, that's E equals mc squared. We're getting it. Finally, similarly, a moving tennis ball has more kinetic energy than a stationary tennis ball, and therefore it should have more mass. And Einstein says, no. What? No. I thought we were understanding E equals mc squared. Einstein, how is this different? You said more energy gives more mass. The moving tennis ball has more energy. It has additional kinetic energy. So why doesn't it have more mass compared to a stationary ball? And the answer that Einstein gives to this, that is the final piece of the puzzle, folks. That is what we need to truly understand what E equals mc squared is. And once we understand this, everything else will logically follow. So are you ready for this? Because this is it. This is the climax. All right, let's do this. Einstein, why do you say that there is no more mass in this case? Well, Einstein says if we go back to the spring case, when we compressed the spring, we added more energy inside the spring. Some internal structure of the spring changed. More energy in the spring, that manifests as more mass. The same thing happens with the coffee. When I added more heat, the internal structure of the molecules change, in the sense they're now vibrating more. There's more energy added inside the coffee, and therefore there is manifests as more mass. But when the tennis ball is moving, Einstein asks, have we added more energy inside the tennis ball? I mean, think about the molecules of the tennis ball. Is that vibrating any faster now? No, the temperature is the same. Is there more potential energy in some sense inside the tennis ball? No, it's not. So we haven't added more energy inside the tennis ball. Another way to think about it, Einstein says, is imagine you want to weigh this tennis ball now. How would you do it? This tennis ball is moving. You have a weighing scale. How would you do it? Well, one way to do that would be to run along that tennis ball with the exact same speed so that the tennis ball appears to be at rest with you, and then you weigh it. But now the tennis ball looks identical to that other stationary tennis ball. In other words, this kinetic energy that you have added to the entire ball does not add more mass to the ball, because you're not adding more energy inside, in some sense, inside the ball. Another way to put this all together, Einstein says, is think of it this way. If you have a moving object, its total energy has two components. It has the energy at rest, the energy that you see from the rest reference frame, and then it has this additional energy of motion, like the kinetic energy of this ball. What really matters is the rest energy, because that's the energy that in some sense represents the energy that's confined inside that object. The energy of the motion doesn't really matter when it comes to mass. And therefore, Einstein says, what matters is this rest energy, and that equals mc squared. Not the total energy, but the energy that's there in the rest, the energy that's inside the object, that equals mc squared. So now we have the tools needed to find the mass of any moving object. First of all, we need to figure out from the total energy, how much of it is the rest energy. And how do you figure out its rest energy? Well, just get it, move along with it at the same speed and look at it from the rest frame, and now calculate all the energy inside it. That's the rest energy. That equals to mc squared, and from there you can calculate its mass. So now that we know how to calculate the mass of a moving object, let's see if we can apply this to photons. First of all, can we see what we did wrong earlier with the photons? When we earlier divided the photon's energy by c squared, we took the total energy of the photons and divided by the c squared. That's why that was a mistake. We need to figure out the rest energy of the photons, divide that by c squared. That gives you the mass of the photon. Let's do that now. Let's do that. All right. Okay, let's move it over here. Here's our photon. I want to figure out what is the rest energy of the photon. How do I do that? Well, just like what we did with the tennis ball, let's move along in the same direction as the photon at the same speed, the speed of light. Wait a second. I will have to move at the speed of light for that photon to appear to be at rest. Einstein, can I move at the speed of light with a weighing scale? Einstein says no. Why not? Because according to special relativity, Einstein says to exert any object to the speed of light, you need to put infinite energy into it. But wait, why does moving at speed of light require infinite energy? Well, you can actually derive this step by step using Einstein's postulates. And what if I told you there was a fun and a free way to actually learn this? Introducing Brilliant.org, this video's sponsor. Brilliant has amazing math, science, computers, and data courses. I love their cool interactive simulations because it makes things super intuitive. I went through the advanced physics section and took their special relativity course. I loved it because it started from the basic Newtonian mechanics, and then using beautiful interactive simulations, I was able to build all the relativistic equations and even derive the famous E equals mc squared. And eventually, I discovered why it takes infinite energy to travel at the speed of light. I and my friends love Brilliant. I also recommend them to my students. And if you want to check it out, then there's a 30-day free trial that you can take. But the first 200 of you can get a 20% lifetime off on annual subscription. All you got to do is follow this link, www.brilliant.org/FloatHeadPhysics. The link is also in the description. Not only will it help you learn things deeply, but you'll also support my channel. All right, back to the video. So you, me, or donkeys will require infinite energy to travel at the speed of light. And therefore, I cannot travel at the speed of photon. I can't do the same thing as I'm doing with that tennis ball. All right? Okay, but Einstein, what if I don't travel at the speed of photons? What if I travel at, like, say 99.99999% at the speed of photons? That's possible. I need finite energy for that. And then I would see the photon to be almost at rest, almost. No, it doesn't work. Because of Einstein's postulate, we already know that from any reference frame, regardless of how fast that frame is traveling, you should always see the speed of light to be c. Photons will always appear to be moving at the speed of light c, and therefore I will never see it to be at rest. I will never see it slowing down. What does that mean? Oh, this means that the photons do not have any rest energy. All the energy of the photon is the energy of the motion. And because they don't have any rest energy, that's why they should have no mass. Because they don't have any rest energy, that's the reason why we say photons are massless. Whew. But I promised you that we're going to look at it from different angles. And there is a way to attack this using a counter argument. Let's do that now, all right? So, Einstein, you said that there is no such thing as mass, right? It's only the energy. So, am I not allowed to define mass as I see fit? So here's my alternate definition of mass. What if I define mass as the total energy divided by c squared? I define it that way. I don't care about rest energy and motion energy. I define it as total energy by c squared. According to this definition, that moving tennis ball will have more mass because it has more total energy, and therefore it should have more mass. And then according to this definition, I should be able to say mass of the photon equals its energy divided by c squared, because look, I no longer care about its rest energy and moving energy, just energy divided by c squared. My question to you, Einstein, is, can I do it this way? Can I redefine my mass to make sure that photons have a mass like this? And Einstein says, yes, we can do it. What? Really? And Einstein says, in fact, this is how we initially interpreted relativity. A lot of scientists took this viewpoint that when you're moving, your mass increases. Feynman also uses it in his lectures. He thinks about how the mass of a body increases with velocity. And I'm like, Einstein, well, then why do we not use this? Because Einstein says, we abandon this idea. Today, we don't use this notion. And I'm like, why? This makes so much sense. Why did we abandon this? Let's calm down a little bit. Einstein says, okay, there's a problem. What's the problem, Einstein? Well, remember how we said that when you accelerate an object to speed of light, it will have infinite energy? Yeah, but now according to this new definition, it should also have infinite mass. And I'm like, cool, so this means in this alternate definition, mass goes to infinity at the speed of light. And I'm cool with that. If energy can go to infinity at speed of light, mass goes to infinity at speed of light. I'm cool with that. What's the problem here, Einstein? Well, Einstein says, but photons have mass according to this definition. They have finite mass and they travel at speed of light. They don't have infinite mass. Oh my God. That's the problem. There is a contradiction. On one hand, we are saying going at the speed of light should give you infinite mass, but photons can go at the speed of light and they have a finite mass according to this viewpoint. Oh my God. So there is a contradiction. So this will not work, is it, Einstein? Einstein says, no, Mahesh, don't sell it short. We can still make it work. In fact, there is a way in which we can make this whole thing self-consistent. The way to do that is we'll define two kinds of mass: rest mass and moving mass. And then all we have to do is agree on two things. One is that things which non-zero rest mass, like you, me, and donkeys, get infinite moving mass at the speed of light. And then things with zero rest mass, like the photons, get a finite moving mass at the speed of light. I'm like, wait, what? I need a second here, folks. Feel free to pause the video. Oh my, what is this? And Einstein says, exactly. This is the problem with using this viewpoint. It is too confusing. You have to cook up two different kinds of masses, and then you'll have to invent different rules for things that have zero rest mass and things that have non-zero rest mass. It is just too darn confusing. In contrast, Einstein says, look at the other viewpoint. Isn't that simpler? Where you just have one type of mass, and that mass is basically the energy content of the system, and that mass does not change with speed. Like, isn't that more intuitive? And isn't it just easier to say that photons don't have mass instead of defining these new rules? Because of this simpler viewpoint, we abandoned this idea. And at this point, Einstein educates us and tells us, remember, Mahesh, physics is not about understanding reality. It's actually about creating models to simulate reality. And sometimes you can have multiple models like you have in front of us. And even though they could be self-consistent, both models are self-consistent, some models are just too darn complicated, and we don't want that. We want a simpler model. That's the reason why we got away with this model. That's why this has become now obsolete. And today we don't talk about moving mass and rest mass. We just talk about mass. That's it. Just one kind of mass. And we say photons are massless. That's the simpler viewpoint. Wow. That's beautiful. Although we have covered pretty much everything now, I promised you we're going to look at it from all possible angles. So Einstein, I have one last question for you. Under this viewpoint, the simpler viewpoint where we say that mass is the amount of rest energy, in this viewpoint, can photons have mass? And Einstein says, yes. What? It's possible light can have mass if photons travel slower than c. What? Photons traveling slower than the speed of photon? What does that even mean? And Einstein replies with something extremely vague. He asks me, Mahesh, what do you think will happen if I slap you? Don't do that, Einstein, but if you slap me, my cheek will hurt. Now Einstein says, him slapping me is the cause and my cheek hurting is the effect. Now, it feels in this case as if the cause and the effect happen at the same time, instantaneous, but turns out, according to relativity, cause itself takes some time to go from one point in space to another. Cause itself has a speed, and the speed of that cause, which we call the speed of causality, that is the ultimate speed limit in the universe. And Einstein says that his theory of relativity is actually not about the speed of light, it's about the speed of causality. Wait a second, Einstein, is that the reason why we have a c? Yes, c is the speed of causality. And so his postulate that nothing can travel faster than the speed of light, or you cannot travel at the speed of light, it actually means you cannot travel at the speed of causality. And in all the different reference frames, it's the speed of causality that stays the same. But then Einstein, why do we talk about speed of light all the time? Well, he says because in this case, the light is the photons are the one that are sort of like the carriers of the cause in most cases. And therefore we think that photons travel at the speed of causality. And therefore everything that applies to causality also applies to photons. But what if that's not true? What if photons are traveling slightly, ever so slightly slower than the actual speed limit, the speed of causality? Then all bets are off. Then you can travel at the speed of photon because you are still traveling slower than the speed of causality. You don't need infinite energy anymore. Then you can find photons at rest, and they will have rest energy, and therefore they will have mass. So does it make sense now why, if photons travel slower than c, they can have mass? So if you put it all together, Einstein, how can we summarize everything that we just learned? And Einstein says we can summarize everything in just 2 sentences. The first one is, things traveling at speed less than c should be massive. And now it makes sense, because if you're traveling less than the speed of causality, you can always find them at rest frame. They will have rest energy, and therefore they will have some mass. And secondly, things traveling at the speed of causality should be massless. That also makes sense, because if you're traveling at the speed of causality, which we think photons do, then they will never be able to become at rest, and therefore they should always have 0 mass. That's the reason why we say photons are massless. We've now looked at things from all possible angles. And that's it, folks. This is it. Did the video live up to the promise? Do you now have a much more profound understanding of why we say photons are massless? Let me know. This is it from my side. See you.